Hello everyone and welcome back to the second part of the OIS discounting curve construction video, the practice part. In the previous video you have, hopefully, learned about the theory. Here we will focus how to apply the theory through a completely self-contained Excel spreadsheet example. That means that every step of the bootstrapping calculations, from the quotes inputs to the discount factors outputs, is present in the spreadsheet. It's 100% Excel and VBA. You don't need anything else than this spreadsheet, and we are not calling any external sort of library. That's the beauty of it. However, for those interested in our open source risk engine C++ library, which we call ORE, we will make direct comparison with some of the main steps of the calculations and the results of these calculations, so you can see a sort of parallel between what's happening in C++ and Excel. And if you want to scale up beyond this OIS curve bootstrapping example, as a reminder, ORE is open source, which means it is entirely free, no string attached, and available right now. Now, if you're already familiar with ORE, and in particular if you're already familiar with the video about the equity option pricing with ORE, the underlying data that we use in this example should be familiar because it's almost exactly the same data. Now, this video is meant to be self-contained. However, if understanding ORE is your primary focus, and if you have not watched it, I would strongly suggest you do that first, as you will understand better the structure of the files needed for such a pricing exercise. You can see the link to it appearing in the top right corner. Now let's dig it into the spreadsheet. So first, let's look at the inputs and in particular the configuration tab. So the configuration tab, these are for general settings. Most importantly, we have the legend for each type of cell. Can guarantee that every single cell of the spreadsheet is accurately represented, but we made an effort to try and do it in order to improve navigations. First, you have the user manual input in orange. This is where your user can change the setting. As you can see on the left, for example, you can change the valuation date. If you want the solver Excel VBA add-in to be installed when you open the workbook, and then there's other settings that we will see later. Then you have the fixed data in dark gray. It's all the non-dynamic / fixed inputs. Here on the left you have some Excel mapping, which is used in some schedule generation formulas, and then you have the ORE inputs data here, conventions, and then market data here. So we also have the data retrieval in teal blue. Those are simply cells referencing other cells with index or just equal functions, and there's no calculation in those cells. Then you have the calculation cells, which are when you have Excel or VBA calculation, as you can see here. And we differentiate these cells from the root finding parameters in turquoise. Those are objective and variables used in the Excel solver for both the interest rate curve and the equity implied volatility curve, as you can see here. And finally, in yellow, we have the output needed, which represent the main outputs and what is written as well in the C++ files. You have those here and you have those here as well, for example. And we also have these three icons, which helps you navigate through ORE with, in blue, the configuration files. That's all the XML inputs. In yellow, the C++ file that takes you directly to the online repository on specific C++ files, and in green, the user files. And I'll show you a few examples during the presentation. And one other thing we have just added before releasing this video, you can remove or add protection on the worksheets. It's activated by default in order to avoid unwanted modifications to the formula, because it's very easy to break things, but it's your choice. If you select true, every single worksheet will be protected. There's no password. If you select false, you'll be able to turn this off. As you can see now, you can access it. And it's also something you can change in the ribbon with review and unprotect sheets. In the market data schemer tab, we have a mapping of what is happening under the hood in ORE. and it shows three main pricing components of an equity option: the equity curve, the equity volatility, and the only focus of today's video, the discounting curve. So we also have the conventions file, which is data directly taken from the ORE convention file, which you can see online here, or you can find a local version of it in your in this example, if you have a local version of ORE. And they are market data conventions usually set by the institutions. For example, if we look at the Euro-Ester OIS instrument, the conventions are set by the European Securities and Market Authorities, the ESMA, and you can find some of the information here. And finally, we have the market data inputs, which is data directly used by the calibration of our discount factor curve, for example, but there's also data for the calibration of the equity implied volatility curve, and obviously for the pricing of the European equity option, which we'll look at in another video. You can also notice on the right some documentation regarding some of the fields. This is taken directly from our ORE user guide. There's also a link to the today's market file, which is where we start building the curve which we need in ORE. And also you have some link to the XML files or the market data file, for example, which you can see will correspond to what we have in this tab. And that's it for the inputs. Now, what we are really interested in this video today is the bootstrapping of the discounting curve in the interest rate curve tab, which is where all the magic is happening. And you may have noticed it, but it's worth pointing it out. There's also a second calibration tab dedicated to the calibration of equity volatility curve. And both calibration tabs are used to price an European equity option and even generate an implied volatility surface. And then there are two additional tabs, which I think is a welcome addition. There's this one, the visuals, where you can visualize some of the data that we calculate. And then there is a pretty substantial ORE C++ call stack, for those who are familiar with the term. It shows the list of functions called within ORE from the start, when we call ORE executable, to the end of both yield curve constructions. And it is meant to help you understand how ORE really works and how all the functions are called in the C++. And it could be useful, for example, if you're interested in knowing where the ester is built, you can just search. And you can see here, the first thing is some of the XML data are parsed. And here, this is where we start building the yield curve Euro-Ester object. And you can go online to find it, or you can link it to your local version of ORE. Just make sure that you are correctly added the path to your engine folder here. If you don't, it will tell you here. And it will directly take you to the file in question, as you can see here. We'll probably do a video specifically dedicated to showing the C++ aspect of ORE, in particular going through the whole stack and explaining what the code does. So if that's something you're interested in, please let me know in the comments or by email. So that's it for the introduction. Now I'm going to start with the market data schemer tab. So just looking at the upper part today, the interest rates, what we're showing here is how the inputs are configured in ORE in order to build the Euro-EONIA discounting curve. As you remember from the theory video, the EONIA curve is actually a zero spread yield curve, and its equivalent zero coupon rate curve is built by adding a spread of 8.5 pips over the Euro-Ester zero coupon rate. The EONIA is built with a single segment, a zero spread segment, which with its convention set in green, its market data in yellow, and which is just a spread, and its reference curve in blue. If we look at its conventions, because in our case the spread is constant, it's 8.5 bips regardless of the tenor of the quote, most parameters set in this convention don't really matter because most of them are used to determine exact quote dates and how to precisely interpolate the zero spreads between those dates, which we don't really need here. However, for your information, you can see the description of all these conventions directly taken from our user guide. The second element that we need is the Ionia Ester spread, which is actually a market data. And you can see here we're actually providing two quotes, an overnight and a 50-year quote, but the tenor of the quotes don't matter at all. This way, and you can see it's the same rates, it's just that this way any interpolation or extrapolation of this spread will be 8.5 bips. This is what we want. And finally, we have a reference to the Euro-Ester curve, which is the curve we are actually bootstrapping. And you can see that this curve is composed of two segments, a deposit segment and an OIS segment. The deposit segment is composed of a single deposit rate and very minimal conventions. The OIS segment, on the other hand, is composed of 36 OIS quotes. Those are swap rates. The only field that we really need, or in the Excel at least, it's the instrument type, the term, and the rate. The tenor just here indicate that it is a overnight instrument, and the forward start, we don't even use it in ORI. Now, regarding the conventions of an OIS, this is where we have some very important information about how they are built, and in particular about how the cash flow schedule is built. And this is where you find all the elements related to the schedule generation chapter in the theory video when we talked about the different graphs, if you remember. So we have the spot lag, that's the start of the OIS, set to 1 business day after the valuation date. The day count convention set to actual 360, used to calculate the cash flow accrual period. Then you have the payment lag set to 1 business day after the end of each cash flow period. The frequency of the cash flows on the fixed lag is annual. Both accrual and payment rule convention is set to modify following, and the construction of the cash flow schedule is set to backward. And that's the whole interest rate schema. For those who are interested in understanding ORI, we already explain, to some extent, the configuration files relationship in some previous videos, and you should see a link to them in the top right corner. But I'll still give a quick recap of what's happening in our case, so this video remains as self-contained as possible. And with that, you will be able to understand where all the data we've just showed is coming from. So we're going to look at 3 different files here: curve config, today's market, and market data, which are all in the input folder. First, the curve config on the right. It can be seen as a sort of library with all the market data configurations that could potentially be needed on any days. So if you're using ORI across a whole bank, this could be common across a whole company, regardless of asset class, or if you're front, middle, or back office. The today's market file, however, defines the list of the market data configuration which you want to build for the specific analytics. Here's just NPV, and it also defines the function of each of these configuration. And when I say function, I mean how it is going to be used, which is different than their nature, let's say, in that case. They are both yield curve. And I'm aware that in the financial world lexicon, yield curve tends to designate specifically a curve built from bonds, but in the case of ORI and Quantlib, its definition is broader than that. So let's go very quickly through this. First, the Ionia acts as the only discounting curve for the equity option, and it is in the curve config file in a yield curve with a S node as a yield curve node without a S. Its segment is of type 0 spread, referencing 2 quotes in the market data file. Its convention is listed here, and under that you can see the decount convention set to 365 days. Then you have also the parameters regarding the interpolation choices and the bootstrapping, for the both of which we'll try to have additional dedicated videos. Then you have the Euro-Ester yield curve, which is set as an index forwarding curve, which per our user guide is used to project index fixings. It's composed, we have seen it multiple times, as 2 segments, a single deposit quote with single deposit quote with this convention, and then you have 36 OIS quotes, which you can see here with this convention. I'm not going to go further than that, but in a nutshell, this is pretty much how it's done in ORE, and I would imagine very similar in most financial libraries. The only difference is that you can see what is happening here because it's open source. Now, we've looked at all the inputs. We are finally ready to tackle the part you have been all waiting for, the actual bootstrapping calculations. As you can see, there are a lot of things happening in this tab, and we are going to start with the buttons on the top left-hand side. Those buttons are always visible, no matter where you are located in the tab, and they allow you to select a quote and trigger the calibration in order to find the implied discount factor for the chosen quote here. The first button is the reset button, and it takes you back to the first quote, the deposit quote. Then you have 2 additional buttons, navigation buttons, which takes you to the next quote or the previous quotes, as you can see here. And you can see in the middle the main information for each quote, with the quote number from 1 to 37, the instrument type, deposit or OIS, the term, and the quote date, which are taken from this table, which itself is just a summary of just information from the market data tab. And then you have also the term and the payment date, both being calculated in this table, and we'll come back to it a little bit later. Then you have the calibration button here, which triggers the root filing algorithm, and you can see both the inputs and the outputs of this algorithm on the right hand side of the tab. And we'll come back to it towards the end of the video, but basically when you're starting the calculation of a quote, the estimated implied discount factor in the cell DF, which stands for discount factor current guess, is originally equal to an initial guess from this cell. We also have the DF real C++ cell, which comes from ORE directly, and which we use as our golden source for the implied discount factor value calculated. And in the difference, you can see how far we are from this reference value. Now, a little reminder about what we are trying to achieve with our root finding algorithm. The goal is to change the value of the implied discount factor until the fair rate is sufficiently close to the value of the swap rate, which is itself coming directly from the quote. And the difference in this cell here show you how far you are. Obviously, this is done in an optimal way, not just randomly, and the way this is done depends on the type of root finding algorithm that we're using. In ORE, we use the one-dimensional Brent algorithm, which uses the inverse quadratic interpolation method and the bisection method. And we will debug this part of the code in Visual Studio later in the video so that you have a better understanding of how it works in ORE and Quantlib. And in Excel, we are using the GRC nonlinear, which is the default setting for the solver. One thing about the solver, if you don't want to allow the Excel VBA add-in, native add-in to be installed because your company have special security restrictions, for example, you can set its installation to false. And the standard goalseek will be used instead. It's just less accurate, that's all. There are also two parameters for the bootstrapping, which is important to mention. First, the accuracy of the root finding algorithm. Here we call it the arbitrage threshold, and it corresponds to the epsilon in this equation or this equation. And in ORI, the accuracy is set to 12 decimal points by default. It's also what we set in the curve config file here. And then there is a second parameters you can change, and it's the objective of the root finding algorithm. And when I say objective, what I really mean is what composes the fx function, which is this or this. And you can choose between red quote and leg NPV. In ORI, it's the red quote which is happening, and it works by trying to match the fair rate with the swap rate. So that's the fair rate calculation. And so in the cell difference here, depending on which setting you choose, it will perform an absolute difference operation from a different source, the current source being indicated with the yellow arrows. And when you choose the leg NPV setting, it performs this operation. It tries to make the floating leg match the fixed leg. And you can see as well here the difference, the arrows points to different cells. We're going to keep the red quote for now. So what happened when you click on launch calibration, this button here? Well, for now you can see that the current guess is equal to the initial guess, and it's still pretty far from the real discount factor value. And you can see as well that the fair rate is pretty far from the swap rate. Now, if I launch the calibration, you can see now that both cells difference indicates 0. It means that the fair rate calculated is very close to the swap rate, and it also means that the implied discount factor that we calculated is very close to the C++1. So we're pretty happy with the result. And then there's the last button, which triggers an animation. And depending on your computer, this might take between 30 seconds and 2 minutes. If you trigger it and it's taking too much time for your liking, you can still stop it midair by pressing the escape key multiple times. What it does is, well, it bootstraps your whole curve in lifetime. It's going to go through each quote one after the other in a chronological order, and for each quote, it's going to run the root finding algorithm in order to find the implied discount factor of this quote. I know, magic. So regarding the upper banner, which by the way is always visible when you go down the tab, there's still the valuation date and the spot date, which we haven't talked about, and those values are fixed. They are not dependent on the current quote. To calculate the spot date, remember it's the valuation date plus the spot lag. So spot lag is coming from the convention, it's coming from here. So the spot lag is 1 business day, but how do you add business days in Excel? It's not that straightforward because you need to account for weekends and holidays, and those depends on the calendar chosen. Each country adds its own public holiday. And for countries like Israel or Saudi Arabia, the weekends are Fridays and Saturdays, not the Sunday. That's why when you look at Quantlib, each calendar is coded in its own file. For our purpose, we have taken the C++ code from Quantlib for the target calendar and translated it into a VBA code to generate all public holidays for 2021 for 60 years. There's only 6 public holidays for the target calendar. 4 of them are always on the same date. The Easter Friday is always 3 days before Easter Monday, and only the later Easter Monday requires a special algorithm to find the date. Alternatively, you can read from a mapping indicating the result of this algorithm with the day number it falls on, which is what we have in the C++ and also in the VBA. So to add business days to a date in Excel, you just use the workday function, passing the list of the holidays generated. That's it. There are also a few data hidden that we brought into this tab. It's just so that everything is handy. So we have explained the whole upper banner, and you can see below some graph displaying the results of the calculation. So you have the zero coupon curve on the left-hand side and the discount curve on the right, representing both the Eonia and in yellow, and the Esther in green. What you can notice is that we also display the data differently up to the previous quotes and the data at the current quote. The reason is at the point Tn, we already have built the curve up to Tn minus 1. So up to the previous quote, we assume that information is known. At Tn, we display 3 different values. The initial guess, which is just a projection at Tn using the zero coupon rate at Tn minus 1. The current guess, which at the beginning of the calculation is equal to the initial guess, and which at the end of the calculation should be very close to the real value taken from the C++, which is the last point. And in between these two states, if we could slow down the root finding algorithm to show all the intermediate values used by the algorithm, we would see the point for the current guess for the Esther and for the Eonia move on the graph. But it's too quick here, so we can only see start and end results. And then you have a third graph, which represents the cash flows of the current instrument. So far, well, the longest instrument is the 60-year OIS quote. That's the quote number 37. We have 60 cash flows every year. We separate the value of the cash flow at time ti, so all these times. So with the non-discounted in yellow negative and positive in green, and the impact of the discount on that same cash flow in orange for negative and blue for positive. And we also display the discounted cash flow on the fixed leg. That's the light blue line. So we have 37 quotes, plus we add one synthetic one representing data at the valuation date. So the first thing we need to do is determine the term date and the payment date for each quote. Not just the current quote, but for all the quotes. So first thing we do, we parse the tenor of each quote and we add it to the spot date without consideration of weekends or holidays. So when you add 1 month to the spot date, which is the 25th of June, you end up with the 25th of July, and it's a Sunday here. Then you add a business day to that date if it's not a business day. We could have put everything into the same cell here, but we wanted to highlight the cases where the term date is actually adjusted with the roll day convention, which is set here to the modify following. And then to calculate the payment date, the payment lag being 1 business day as per the convention, you add 1 business day to each term date. The first 2 quotes are exception. That's why they are presented with different colors, because we add their term to the valuation date rather than the spot date, and also there's no payment lag. The next step is then to transform this payment, the payment date, into year fraction using the actual 365 day count as set in the curve config. And it is not to be confused with the OIS day count convention, which is set to actual 360 days. This convention will only be used for the calculation of the cash flow periods, not when discounting these same cash flows. So this is how we calculate it, and then you have the calculate column, which is just here to indicate which quote we show. So if we go back to the tens quote, for example, you can see that it's true up to that quote. So next step is to, so we're going to skip this table for now. We're going to go to this one, and it's to determine the cash flows of the instrument represented by each quote. And the end goal is to calculate the value for each leg given, so that you have floating leg and fixed leg. So given the current guess of the discount factor at the payment date for this instrument. And you can see we brought a copy of those cells here, just so you can see everything at once. You can also see a table here which is used to determine the number of cash flows of the instrument, and so you have number of complete period, and also if the first cash flow has an odd length, so less than a year. And then we will show you a few different situations which correspond to this graph, which you should remember from the previous videos. So the first case is pretty simple. We're going to go back to the deposit case, and we're going to look at here. In that case, it's pretty simple. There's only one coupon. The cash flow period starts at the valuation date on the 24th of June and end one business day later on the 25th of June. And there is no payment lag, so the payment date is also the 25th of June. Then we need to calculate the coupon accrual period, and this will be used in the calculation of the cash flow value of both fixed and floating leg. And this is where we use the actual 360-day count conversion set for both deposits and OIS that we talked earlier. The next two values we are going to need are the discount factor at the end of each period and the discount factor at the payment date. And you can see that we're doing some interpolation here. It's because potentially they are not already part of the pool of the discount factor that we already calculated and which you can find here. Now obviously for the first quote there is nothing to interpolate because beside the discount factor at T0, which is 1, the only discount factor that we need is the implied discount factor for this particular quote. But when there is a case where interpolation is needed, I will show you. However, as a reminder, this is the formula for the log linear interpolation. And because the choice of interpolation can be different for each term structure, in ORE we parameterize it in the curve config file, which I'm going to show you now. There are 3 parameters driving the interpolation. First, the interpolation variable, which can be either discount, so on the discount factor curve, 0 on the continuously compounded 0 rate, or forward, so it will be on the instantaneous forward rate. Then you have the interpolation method, which represents the type of interpolation method that you want to use, and you have quite a few. This is probably going to be the subject of a future video where we'll show the impact of the choice of different type of interpolation on the term structure, so stay tuned. And then you have the extrapolation, which allows or not the use of extrapolation. If it's set to false, it will just keep it flat. And if you want to check the documentation, you can look at chapter 7.81. You have the description of the field, and you have the different description of different values, including the list of interpolation method here. The next value we need is the compounding factor, which represents how much you get at the end of the coupon period when you invest 1 at the start of the coupon period, and which is calculated by dividing the discount factor at the start of the coupon period divided by the discount factor at the end of the coupon period. So it's going to be 1 divided by this in our case here. And then you have the column duration, which is not exactly duration, but I didn't really know how to call it otherwise. And it's just the coupon accrual period time the discount factor at the payment date. Now, while the fixed rate is directly the quote rate, the floating rate, also called swaplet rate here, with the formula that you have seen in the previous video, so it's this one. So it's the compounded factor minus 1 divided by the coupon accrual period. And given that, we can now finally calculate the discounted cash flows on both sides of the swap. And they are both calculated the same way, with the floating rate or the fixed rate, depending on the leg, multiplied by the coupon accrual period to obtain the value of the cash flow, multiplied by the discount factor from the coupon payment date to the valuation date. And you can see the formulas, which are both here. So it's going to be this part. And because we only have one cash flow, here the NPV of each leg is equal to its respective discounted cash flow. And at the beginning of the root finding algorithm, both legs should have different values, as you can see, because the discount factor that we use is not correct yet. Before running the root finding algorithm in Excel, I would like to show you how all these calculations look like in ORE. And to get a decent overview without going in too deep into the C++ code, we are going to place ourselves with some breakpoints in the Brent root finding algorithm function. You can click here to see it online, or you can use the call stack to access the file locally. So if you do Brent, you would find it here. And if you have a local version of ORE, I would recommend doing it because you will be able to follow the steps that I'm showing you. And if you're wondering how to debug ORE in Visual Studio, we have a short video which shows you how to do this. But basically, all you need to do is set your debug targets to the ORE executable, and then set up these arguments so that ORE points to the example you want to run. Here, as mentioned at the beginning of the video, the whole spreadsheet is based on the equity option pricing video and the data used for it. And we're going to try and reuse as much as possible the same data in all the videos so that it feels familiar. So looking at the Brent function, and let's launch the debug meanwhile so we can do some digging later. First, the inputs. It works by passing a function f, the objective function, and a level of accuracy, which is just or epsilon, and it's 1 power of minus 12. So the objective function f of the root finding algorithm represents the absolute difference between it represents the absolute difference between the fair rate, which is here, or called the implied quote, and the swap rate. In other words, it's how close we are from the target value. Now, most root finding algorithm will be composed of a loop, as you can see here. It's a while loop with two possible exit scenarios. So either the maximum number of iteration is reached, is this to avoid infinite loops, and here it's set to 100, so k is the iteration number. Either the objective condition is met, and you can see here this is f of x, with x being the root, f the objective function, and epsilon the accuracy. And most root finding algorithms work in a similar way. Is my objective condition met? If yes, so we test it here. Yes, I exit and I return the root value, which is the x in the fx equation, which in our case is the implied discount factor of a quote. If the objective condition is not met, then I continue and I change the value of x. Here I change the value of root for the next iteration, And then I try again until my objective criteria is met, or I reach the maximum number of iterations. Now, what makes all route finding algorithms different from one another is how you determine your next X. And everything you see in the middle here is particular to the Brent algorithm. Very quickly, it does an inverse quadratic interpolation. It checks if it's within boundaries, so the mean and the max, which is also adjusted at each iteration. And if it's not, if the interpolation is not satisfactory, then we use the bisection method. And then finally, when the objective criteria is met, then we exit the function, and it means that we're good. So let's start from the beginning of the route finding algorithm, before even entering the loop. Here we do an initial calculation of the objective function using the initial guess. Now, the initial guess, it's used to improve the efficiency of the route finding algorithms, and it aims to provide a close enough guess of where the value might end up. So the first guess, here we haven't calculated any discount factor yet, so we use a simple rate of 5%. And for all other quotes, we use an exponential rate with using the previous zero coupon rate. It's pretty simple. And here we can check the value that we use. Here, it's the same value as here. And let's dig into the objective function in the code. So it takes us to this function and then to this quote error function. And you can see here, this is just the absolute difference between the quote value, which is the swap rate, and the implied quote, which is the fair rate. Now, if we look at it from a formula perspective, and if we add the different scenarios of x at each iteration k, we have this type of formula for the objective function f, with j of xk being the fair rate, b the swap rate, which is fixed, and xk being the implied discount factor at iteration k. Now the quote value, or the swap rate here, is fixed no matter the iteration. What changes is the implied quote, the fair rate, because our xk changes, and it changes at each iteration of the algorithm. Now, if we were to be more accurate in terms of notations, we should probably express our fair rate, which is actually the estimated fixed rate. That's why we express it with a hat. Now, we should express our fair rate in function of the implied discount factor for the final payment date of the instrument at the current iteration k. And it would look like this, which is a lot. And if you're a mathematics purist, I've got a feeling that this might burn your eyes, as I'm sure there's a more appropriate way to express all this, but I hope you get the gist. And so in the end, for notation purpose, we express it this way. And if you want to dig through the formulas a little bit more in details, I invite you to watch or rewatch the theory video about bootstrapping. And this was a sort of summary of what is happening with the objective function here, and here the details of how to calculate the fair rate in function of the discount factor for the last payment date. So if we continue digging into the C++ very quickly, while having the Excel call stack below the C++ call stack and some of the main variables in the watch window, you can see here we are in the Brent file, the solve implied function. If we dig through it, we appear in this one, then this one. And this quote error function appears 3 times in the Excel call stack. First, to get the quote value, the swap rate. Second time to get the implied quote, so that's the fair rate. And the third time to actually calculate the value of an objective function, so the quote value minus the implied quote. So we recover the swap rate of the quote, then we're back to this function, and then finally to the juicy part, the calculation of the fair rate. And in this function, we retrieve an equation we know well, the floating rate equation. So first you get the discount factor for the beginning of the coupon period, the 24th of June. Then you get the discount factor for the maturity date, that's the 25th of June. And then the division of the first discount factor by the second correspond to the compound factor, -1 divided by the coupon accrual period. And this is our floating rate, also called the swap rate. And just to show the correspondence with the Excel spreadsheet, you can see that this function corresponds to very obviously to this formula. And then some of the values. So we have D1, 24th of June, you get D2, the 25th of June, you get the coupon accrual period, you get the discount factor at the end of the period. This one is going to be equal to 1 because that's the discount factor at T0. The compound factor, you won't see it, but it's this value. And then you get finally the floating rate, which will be seen in as a result here. That's the result, that's the floating rate calculated. And for deposits, but also for all OIS with only a single cash flow, you can do the math. That's also the fair rate. So there's no additional steps required in this case. And so we're back to the Brent algorithm after having done one iteration, and we can do a summary of the values which are relevant at that point for our algorithm. And in this table, we have the iteration number. In the C++, you can see the evaluation number. They count the calculation of the objective function for the max and the min, which is done before we even enter into the Brent algorithm. So we start already at the third iteration. So we have the implied discount factor that you have here, that's the root. We have the fair rate, which we showed a few seconds ago. And then we have the objective function, that's f root, which is equal to this, just remove the minus. And then finally we have the column is the objective reached. And you can see here it's way above the accuracy threshold. So we continue iterating. And in the Excel, we will have corresponding values at the first iteration and at the last iterations. But in between, the GRC nonlinear is a different algorithm than the Brent. So all intermediary X values, so at each iteration, will be different. And we can see here the implied discount factor. That's going to be this one, which is taken from this one. Then we have the fair rate, which is calculated here. And finally, we have the objective function here. So that's for the first iteration using the initial guess. And so if we continue in the code, we finally get in the loop. Here we increment our root. So we're changing for the next iteration. And here we assess it a second time. So when here we are at iteration number 2 and or number 4 in the C++, but you can see the different values. So the root here, the fair rate, that was an intermediary value, and the objective function is equal to this one. And you can see it is still far off from the accuracy wished. And if we go back to the requirement again, go to the next one, and then finally go to the false, and we can see here that the objective function value is less than the accuracy desired, which is good, and so we can exit the loop and return the implied discount factor as a result. And we can go back to the Excel and finally run the calculation, and you're going to see those values changing, and we can see that now the difference is close to 0. The discount factor at payment date is equal to this. The swap rate is equal to this. And the objective function will be slightly different, but it's close to 0. And as a reminder, both legs NPV need to be equal so that the NPV of the swap is equal to 0. That's a prerogative due to the non-arbitrage rule. And you can see here that's the case. And that's pretty much the essence of it, at least for the first iteration. And we are pretty much at the end of it. But I still wanted to show you how it works with the OIS, because there are three different cases, as we have seen in the theory video. When the term of the quote is less or equal than a year, which means there's only one cash flow. And when the term is more than a year, which means we have multiple cash flows. But in that case, there are two different situations possible. We only have full yearly cash flows, or we have a partial cash flow at the first cash flows. So if we go to the second quote, which is a 1 week OIS, so that means we are in this situation. You can see the date here. So the start of the period is the 25th of June. The end of the period is the 1 week later on the Friday. The payment date is 3 days later because it's correspond to 1 business days. And then the rest of the calculations are very similar. And you can see we run the calculation, everything works fine too. And if we look at the first multiple cash flow quote, so it's going to be this one, you can see that the first period is 3 months. It starts on the 25th of June and end in September, and then with the payment date on the 28th, so 1 business day after. And the second period, which this one is complete because we're going backward in our cash flow construction, and this second period starts at the end of the first period and 1 year later. And you can see that on the floating leg, each cash flow period will have its own floating rate, whereas the fixed rate stays fixed, and the NPV float is the sum of all the discounted cash flows. And if we look at the, let's say, 2-year term, we can see that both have 1 year period. Now the rest of the spreadsheet is secondary. This table is used to store the data. Here on the left you have the C++ data, which by the way you can easily output by setting up the curve analytic in the master file to be active. Now the first 4 lines will define the settings to output in the curve.csv file here, and this is where you'll have all curve data outputted, but on an artificial grid. You can see here it's 240 data with a monthly frequency. This is what is set up in here. Now to output, let's say, the raw calibrated data, the direct output of your calibration, you can set this optional parameter, output today's market calibration, to yes. And this will be outputted in the today's market calibration file. And it's immensely useful. We don't want to debug the code, find where the data is constructed, check the local variables, etc. Now you just output this file and you check your intermediary results. For the Ester curve, just look at the discount factor for Ester, and you will find that we have over 37 quotes. This will match the value that we have in Excel, in C++, of course. For the Eonia curve, this is going to be slightly different because you can see that we only have 14 quotes with slightly different dates. And that's something we will talk about in the next video, where this data is actually used in the calibration and pricing of an equity option. And it's because this curve doesn't have any pillar dates of its own, and it uses a default set of tenors, as you can see here. So back to our table in Excel. This here is indeed from the Excel, but this is only generated when you launch the full animation. It will run the bootstrapping, the root finding algorithm for each quote, and then save the result here. This here, this source, this is what is actually used by this table, and it's here, and this is what is being used by the interpolation here. So it's quite important to remember that. However, you can change the source of the data used. You can change it to the C++ data in order to compare the result. And here, this is going to take the data of the C++, except for the current quote, which will be coming from here. And what I forgot to mention as well is the calculation of the Ionia, because once you get your ester discount factor curve, you want to transform it into the Euro Ionia discount factor curve, because this is what's going to be used by both the calibration and the pricing of the equity option. And this is done directly in the discount factor column, where you add 8.5 bips to the Euro ester yield rate, and you transform that into a discount factor. And we're just verifying here that this minus this is well equal to 8.5 bips. And then in this table, if I just go up to the last quote, you can see that for the last at 60 year, there's 60 cash flows here. And the last table, those are used by the graphs, so I'm not gonna go through them. You can dig through them on your own. In here it's because I haven't run the bootstrapping. Here we go, we get our curves. In the visuals, there's it's pretty much the same curve, just here you can really see the yield curve with the 8.5 bips above the ester. And one last thing before I finish, you can see in the stack there are way more steps to calculate an OIS swap than for a deposit. And I will just take you to the quote rate again in the code. So from the same Brent algorithm, here we are at the quote number 2. If I dig through this function, it takes us once again here and once again here. However, from this function, this implied quote is going to take us to a different place, where you will recognize the calculation of the fair rate, with here the NPV divided by the fixed leg BPS, which is what I called the duration. Fixed rate here is 0. Now this is where the interesting parts start. I'm not going to go through it. This is where the NPV and all other metrics of the OIS is calculated. And this concludes the OIS discounting curve construction video, the practice part. I hope you enjoyed this type of video mixing general knowledge, mathematical theory, and the demonstration of our C++ code through an Excel parallel implementation. If you did, please like the video and subscribe to our channel. We need the support and we need to know what we are doing is working. As you could have guessed, the next video will be about the calibration of an equity volatility curve using the exact same spreadsheet, and then we'll extend it to show how sensitivities calculations are performed and also parametric VAR. Thanks for watching. See you soon.